Here is the solution to K3. Johanna jogs along a straight path. We're given a table with her velocity data for that jog, and they want us to use the data in the table to estimate the value of v prime of 16. This is v. We'll talk about units later. This is v. They want us to approximate the derivative of v using a table. So what do we have to do? We're thinking slope here. 16's right in this interval right here. So rise over run. Perfect. What about the units? Well, v is in meters per minute. And so we're taking meters per minute, the rise, divided by minutes. That's meters per minute, or meters per second squared. It doesn't look like units were worth a point there, but it's worth thinking about. Part B, though, starts off by saying, using correct units, explain the meaning of this definite integral. So it's the integral from 0 to 40 of, the absolute value of a velocity function. Well, if the absolute value wasn't there, the antiderivative, or the definite integral, I should say, from 0 to 40 of v, just plain v, is displacement. The difference in position from where you started to where you finished. What happens when you put absolute value in there? Well, the absolute value of velocity is speed. When you find the definite integral of speed, you get distance. Essentially, it counts positive and negative velocities as positive. So even when you're going backward, you're increasing in distance, though you are actually decreasing in displacement. That's what the absolute value does. It changes the definite integral from a displacement using velocity to a distance using speed. So, what are the units on there? Well, the velocity is in meters per minute, so is the absolute value of velocity, but it's meters per minute, don't forget the dt, times minutes, so that's just plain meters. We also need to use a right Riemann sum. Remember, that's rectangular sums with 4 subintervals, right with 4. So what are we going to do? Well, here's the first rectangle right here. We're going to use 200 as the height, and the width is 12. So there's a height, there's a height, there's a height, there's a height. The only sort of twist there is that this negative height, we're going to treat it as positive. We're going to change it into positive because we're taking the absolute values of all of these velocities. One other thing to note, whenever you're finding a rectangular sum or a trapezoidal sum or something like that, make sure you show your work. You don't necessarily have to put v of 12, v of 20. This line right here would have been sufficient for showing your work. Okay, so they get that. That's essentially arithmetic. Now on to Bob. They also give you a velocity function for Bob, but now they give it to you in symbolic form, not in a tabular form. What do we want to know? What's Bob's acceleration at time t equal 5? Well, I'm hoping that you know that to go from velocity, which we have, to acceleration, which we want, it's a derivative. So a better way to say it, the derivative of a velocity function is the acceleration function. So we take the derivative and we plug in 5. Pretty easy problem. Very good example of, this is all the way into part C. Maybe you didn't know how to do A, maybe you didn't know how to do B, but keep going because perhaps you can do part C. All right, finally, for D, based on that model, find Bob's average velocity during the interval. Well, they gave us a velocity and they want an average velocity between 2 times, or for a time interval. That's screaming, find the average value of the function between 0 and 10. How do you do that? That's a formula. There it is, average value of the function, 1 over b minus a times the integral from a to b. So that's all they're doing there. The antiderivative is pretty easy. A little bit of arithmetic. That's kind of it. That's the solution to K3.